All right, so let's do sapling. This is number 31. It says CH3, CH2, CCH, and it's saying step 1 is Na, NH2. Step 2 is CH3, CH2, CH2Br. They want to know what the product is. They want to know the product name. So the first thing I would do is get out of this CH3, CH2, CC stuff. I would start drawing it like the stick figures, right? Well, first I would actually number my carbons because that's what you're supposed to do. Draw the alkyne first, all right? Make sure you have the correct bond angle. This would be 1, 2, 3, 4. Notice this is a terminal alkyne. What do we know about terminal alkynes? We can add carbons to them and they're acidic. Right? So let's go ahead and draw the H on there. NaNH2 is a strong base. Do not get this confused with Na and the NH3, the lithium one. Right? I'll highlight that in a little bit. But that's when people get confused. They confuse these things with each other, the different reagents. NaNH2 is this is a strong base, right? Nitrogen with a negative charge is a strong base. Also, again, notice step 1, step 2, right? Don't mix your steps up, right? Don't mix your steps up. Step 1, step 2, it matters.
And what is the NaNH3?
It's a strong base. Oh no, NaNH3 is something else. That's a way to get trans alkenes from alkynes. But I'll show you that, right? So yeah, I can just write, why not? So this is a strong base, right? Whereas Na or lithium, these are solids. These are solid metals, right? These are, you could put S there, right? These are solids. They're the ones that donate 1 electron, right? Like lithium metal on the periodic table or sodium metal has 1 electron to give. Whereas here, right, this is Na plus, NH2 minus. Right, so it's different. This is like the solid, the metal goes in. And they do these reactions, right? Underneath the arrow, you see NH3 or some sort of base, some sort of NH. And this is the solvent and provides a hydrogen for the reaction. But notice how these are different, right? So be careful, right? NH3 is different than NH2. Na plus, or Na next to NH2, is different than Na solid. But people will for sure get this confused. Right? But they are different. That's why we showed you lithium first, actually. In the years of doing this, when we show sodium first, people get confused. That's why we showed you lithium first, like lithium dot. Right? Good. Okay. So we have this one with a strong base. So we just got done saying that alkynes are acidic. So let's have the electrons from the strong base, right? Take the hydrogen, and these electrons go to carbon 4. One, two, three, 4. Of course, we know that alkynes are acidic because the electrons go in an sp hybrid orbital, which is close to the nucleus, right? So it forms a more stable alkyne intermediate conjugate base. Right? This is a strong bond. The CH bond is strong, but the product that it forms is pretty stable. Right? So once we do that, what else do we make? Let's balance our charges. So there's Na plus floating around, right? So don't forget ionic bonds, right? We've been talking a lot about covalent bonds, but the bond between Na and NH2 here, that's an ionic bond, right? There's a plus charge and a minus charge. It's an ionic bond. This is a covalent bond. The new bond we form, right, you can think of it both as, the problem is there's not like this hard line, right? It doesn't change how it reacts, right? The carbon 4 has electron density. That's where the nucleophile is at, right? It's just like a polar bond. Right, so if carbon is bonded to a metal or near and next to a metal, the carbon is the nucleophile, right? Carbon is more electronegative than the metals. Right? So that's the way to think about it. I'm going to redraw 2 here, right? Because that's a 1, 2, 3 carbon piece. Put the bromine on there. 5, 6, 7. So which carbon of our electrophile, right? So we've hopefully established this is our nucleophile, has a negative charge. which carbon of our electrophile is going to be delta plus? 7. So start to think about that, right? If you need to add a 3-carbon piece, right? If you need to make a carbon delta plus, what are you going to have it bonded to? Right? Something that's more electronegative than it, right? Just the opposite of what it's going to talk about. So have it bonded to bromine. All right, so if the electrons attack carbon 7, and then have bromine take those other electrons. And this is why numbering becomes really important. Because if you have a good numbering system, you can't screw it up. Right? So this is a lot harder. It's not impossible. It's harder. 1, 2, 3, 4, 7, 6, 5. And now to balance my charge, I end up with Na plus and Br minus. The cool thing about this, right, if you run this in an organic solvent, right, the NaBr comes out of solution like NaCl would. Right? So it actually pushes the equilibrium. You can actually tell when the reaction is working because you'll see a white solid on the bottom of the flask. There you go. I would add one more thing, right? So NaNH2 is one of the strong bases you use. The other one is that butyl lithium, which you talked about in class. Right? The 4-carbon piece of the carbon with a negative charge, that can also be used to deprotonate terminal alkynes. Okay, so let's do number 24. It's been kind of confusing for people. It says H2 and Lindlars. All right, and that gives you compound B. And then they're saying you treat it with ozone, which we know. Right? We know what ozone does, right? What does ozone do to alkenes? It turns alkenes, right? It's like a scissors. It cuts the alkene in half and makes 2 carbonyls on either side. But then there's this new thing, H2O2, which is hydrogen peroxide, which is an oxidant. But what the product they're showing us is this. They're saying it's succinic acid. And they're showing there's 2, now this is important, there's 2 formic acids. Right, they're showing there's 2 formic acids. And they're also saying over here, H2 palladium on carbon turns this into hexane. Okay. So we got to figure out what's the starting material. So if H2 palladium on carbon turns something into hexanes, right? I mean, this is chapter 7, so we've been talking a lot about alkynes, so it's pretty safe to assume that probably the thing we're talking about is an alkyne. What do you think, and how many carbons does the alkyne have?
6.
Right, 6, I would say, right? So we know it's an alkyne. We know it has 6 carbons, right? We know that because hexane has 6 carbons, right? So if you treat an alkyne with palladium on carbon, it reduces all the pi bonds, right? And you get an alkane, and we don't lose carbons, right? I haven't shown you a reaction where you lose a carbon yet, have I? Nope. So a hexane makes sense. So it's an alkyne, has 6 carbons. What do you guys think B is? What does Lindlar's catalyst do? Lindlar's takes an alkyne and turns it into a
Alkene.
and specifically what kind of addition, right? So we know B is going to be an alkene, and we know Lindlar's does a cis addition. Good. We know what O3 does. O3, right, takes an alkene and turns it into a carbonyl. So let's just number some carbons. Let's say 1, 2, 3, 4, and then 5, and I'm going to redraw one, right? Because it says there's 2 of them. Let's just draw another one. There's 6. Well, I have 6 carbons in my end product, right? So the question is, how did these guys come together? How did they piece together? Right? Well, if you work backwards, right? So you've done this before with O3. If you want to find the starting material from an ozonolysis and O3 reaction, what did you do? You took the carbonyl pieces and stuck them back together, right? As alkenes. So in this case, what bonds would you want to form? What new double bonds would you form between which 2 carbons? 1 and 5 and 4 and 6, right? Or some variation of that. So I think compound B looks like this. Right? If I renumber my carbons, I'd say this is 1, 2, 3, 4. I'll make that one 5 and this one 6. Working one step back. Now I know you guys don't know how to make carboxylic acids. That's this extra reagent, right? So ideally, if I would just have this be ketones or aldehydes here, but you still should be able to go back one step and kind of ignore that right now. Do we see that? Right? How ozonolysis, if we clip the bond there, we'd end up with a 1 carbon piece. Right? 5 and 6 would be 1 carbon pieces that are now carbonyls. Right? So now if I have this alkene, what alkyne did that alkene come from? Where would I have where would the pi bond, where would the triple bonds be between which carbons?
6 and 1.
6 and 1 and 4 and 5. All right, everybody see that? Right? Right, can you make alkenes from alkynes? Yeah, one of the ways is H2 Lindlar's catalyst. The other way is that lithium metal or sodium metal and in a solvent of NH3. All right, so we go back one step and we see the final, what it actually was. We number our carbons 6, 1, 2, 3, 4, 5. So that's the actual product. All right, and that's how I'd want to work back, right? So this comes back to, right, take your reaction sheet. First of all, everybody should have a reaction sheet. I'm going to start asking for it. Bring it with you, right? Have it with you. I'll always check it, but you need to have that done, right? And then now what I want you to do with your reaction sheet is cover with your hand the starting materials and look at the products and say, how do I make an alkene, a cis alkene? Right? And then once you figure out, right, and you know the reagents, and then you can say, oh, I know it comes from that alkyne, then take your hand, cover the starting material, and cover the reagents. Right? First thing, cover the starting materials, so you can see the reagents and the products. Once you got that down, cover the reagents and the starting materials, and see if you can figure it out. Right? Be asking yourself, right, how do I make this? Right? What starting material did this come from? What reagents were used to make this? Okay, so let's start with an alkyne, and let's say we have Na solid, and the solvent is NH3. So Na solid has a lone electron, right? Sodium metal, lithium metal has a 1 valence electron. So ideally, before you even start this, even if you don't know the mechanism, you should be able to draw out the product, right? Because you've been practicing. And you should say, well, I know sodium metal and NH3 is going to give me what? A trans alkene, right off the bat. A trans addition, right? It's going to be a trans alkene. So, of course, first 1, 2, 3, 4. So it certainly helps if we know, right, the product, right? We know where we're going now. We know what we need to get to. Right, so we need to add NHs, or H, we need to break NH bonds. And remember, the other product of this is 2, in this case, Na NH2s. This is part of why people get confused, is because the product of this reaction is actually the strong base that's used in the deprotonation of terminal alkynes. Right? All right, so we have our 1 electron, and we have this pi bond. And we're going to start moving radical arrows again. Now, carbon 2 and 3 are basically, no, not basically, they are the same. They are the same. So this electron, an electron in sodium, and the electron is going to go to carbon 2. Fishhook arrows, right? Not double-headed arrows, fishhook arrows, single-headed arrows. So what do we end up with? We have a dot. Right, how many electrons in a bond? So when you see this electron and that electron come together, what do you think they make? A bond. Albeit kind of an ionic bond, but we'll draw it as a bond anyways. Number our carbons, 1, 2, 3, and 4. Right, so this is that time, right, where we got to remember chapter 1, chapter 2 or 3 maybe. Right? When you're in a bond, somebody hogs the electrons and somebody doesn't usually, right? And that how polar that bond is based on the electronegativities of the periodic table. Right, so usually carbon kind of got bullied around, right? Well, if carbon's bonded to sodium or lithium, carbon's more electronegative. Now carbon has the electron density, right? Notice these guys are trans because there's some electrons here and electrons here. They want to be away from each other. So automatically get ourselves in that trans conformation, right? Methyls apart here. And we know we need to put an NH there, right? 3 needs to have an NH. Only place we can get the H's from is the NH3. And that works because we know we need to make NH2 minus anyways. So these electrons in this carbon-3 sodium bond, ionic bond, both of them are going to attack the nitrogen of NH3. Also, I'd make sure to remind you, when you see Na at the top or lithium as a solid, it's in excess. Right? You literally throw a cube of this stuff in there. And if you want to have fun, look up sodium in water on YouTube. Yep, good times. Potassium's crazy actually too. So yeah, it explodes. It'll light on fire in water. You have to store this stuff in hexanes and oil. It's really cool. But I've done it before. You cut this stuff. It's fun. So now we have that. We have our new H bond. Number our carbons 1, 2, 3, 4. We essentially repeat the process because we have enough sodium metal lying around, right? That again, these 2 electrons can come together. 2 electrons form a bond. So now we have a carbon Na bond. 1, 2, 3, 4. And we essentially do the same thing again, right? NH3 is our solvent, so there's plenty of that around, right? Even though NH3, right, is NH3 a very good base, is NH3 a very good acid? No. But carbon with a negative charge, especially an sp2 carbon with a negative charge, is that pretty reactive? Yeah, right? Yeah. So you actually have to do these reactions at minus 78. Sometimes you'll see minus 78 degrees C, which is a dry ice and acetone. So when we do these reactions, it'd be really cold, otherwise it gets too violent. It's too much heat given off. So then we have another molecule of NH3 rolling around. Oops. Also go back here, right? We also made an Na plus NH2 minus here, right? That step, balance our charges. Right? That came from Na, which lost 2 electrons. And then the NH2 that's over here now. So these electrons between the sodium and the carbon 2 go there. And that gets us, we made another molecule of Na, NH2, the salt, that with the ionic bond. And now we have the trans alkene formed. Right? 2 sets of reagents. But let's compare them by what we want to make. Right? Let's say you want to make an aldehyde. Right? I want to make an aldehyde, or I want to make a ketone. 1, 2, 3, 1, 2, 3. I can make an aldehyde or a ketone from the same alkyne. So what has to be different? If I use the same starting material, I have to use a different set of reagents, right? So the first thing I would look at, right? I got to go 1 step back. So what's 1 step back? Actually, it doesn't. I can do well. I want to say 1 step back, but let's remember. Sometimes it's easier to see it this way. Ketones and aldehydes can be they can tautomerize, right? A ketone has a tautomer. And so does an aldehyde. What does the ketone's tautomer look like, and how does that work? So let's look at this mechanism. Essentially what a tautomer is when the hydrogen on this carbon, which is one away from the carbonyl carbon. They call it the alpha carbon, right? This hydrogen is now on the oxygen, and now there's a pi bond between 1 and 2 instead of the pi bond between 2 and 0, 2 and O. So the mechanism, right? I've shown you the way to take an enol and turn it into a ketone, but what about the other direction? Can we draw that mechanism too? Sure we can. Let's have this pi bond take that H. And now have this H go down. Those electrons between that CH bond go down. So where's the new pi bond? So there's still an O. And still 1, 2, 3. There's an H off the oxygen. And where's the pi bond? Between 1 and 2. All right, we can see that. These electrons, these two electrons here, went and grabbed the H. Those are now there. The electrons between C1 and H are now here. So this is the enol of this ketone. And maybe it'll make more sense in a second why I showed you that. Right? Because you guys have been trained to know what a Markovnikov product looks like. You've also been trained to know what an anti-Markovnikov product looks like. So what is the Enol Tautomer? We can draw that mechanism out over here too. Right? Off carbon 2, again, the electrons between the CO pi bond attack, and then these electrons go between carbon 2 and 3. So now the O has an H bonded to it, and there's now a pi bond there. 1, 2, 3. If you were to look at these two Enol Tautomers, the OH, right, the functional group, the thing you added, is on which carbon? The more substituted or less substituted? This one's the more substituted. On this one, from the aldehyde, when you look at the enol, the OH ends up on the less substituted. So you recognize that as being the anti-Markovnikov product, right? This is like an anti-Mark product, or this is a Mark product. Right, so maybe it's hard to see from the aldehyde and ketone, but the tautomer kind of gives it away. So now my question is, now let's do the retrosynthetic arrow. Where would the pi bond be? Where would the alkyne be between which two carbons? Where's the alkyne? 1 and 2. Always draw the alkyne first and then draw the carbons after that. And what about for this guy? For the aldehyde? I mean, it's between 2 and 3, but really it's the same, right? It's all a matter of perspective, right? It's really the same. My numbering is my numbers is just different a little bit. Okay. So that's working backwards. That's identifying I have an enol and the OH is on the more substituted carbon. What alkyne did that come from? Right, what alkyne does this come from? Now what reagents do we need going this direction, right? So this is working backwards. So now going forwards, what reagents do I need to get that enol, to have the OH on the more substituted carbon? What reagents would I need? There's two options.
Either the mercury.
I would say the mercury 2 plus.
H plus and water.
H plus and water. Or just H plus and water. Right? That would give me that. What if I want to get the OH on the less substituted carbon? What would that be? A boron, usually we say BH3, and that's step 1. And then step 2 is OH minus H2O2. Good. Usually it's water. Yeah, but you get the gist of it. That gives you the anti-Markovnikov product. So far so good there? Makes sense? But I know this question exists on sapling. I don't know if anybody's caught this yet. What happens if I take this alkyne and I just want to get this? How many different ways do you know how to do that? if you treated this alkyne with BH3 and then OH minus H2O2.
And you do it, either way would be the same.
Either way, it's the same. There's no preference, but still, BH3 doesn't just work for terminal alkynes. It's regioselective for terminal, right? If you have a terminal alkyne, right, with BH3, you'll get the aldehyde. You get the anti-Markovnikov product. But if you have an internal alkyne, BH3 will still work, but it's going to give you a ketone. Right? These guys still work too, but now you have 1, 2, 3 ways to make ketones from internal alkynes. I know that was a question on sapling. That's a good one to catch, right? It doesn't matter. It still works, right? It still works. The other thing that's confusing is what if your alkyne wasn't symmetrical? So what if I had an alkyne like this? If I number my carbons 1, 2, 3, 4, and 5,
Is it still the same?
are 3 and 4 the same?
Well, because they are bonded. They're each bonded to one other carbon.
How many carbons show up in a C13 in that molecule?
Well, they're not the same.
So they would lead to different ketones then. Right? So this is the other point I wanted to make. Right?
Wait, even though
Internal alkyne, that's symmetrical, right? Has 1, 2 types of carbons. It's symmetrical. You can split it down the middle. This alkyne is not symmetrical. Right? Carbon 3 is different than carbon 4. Carbon 3 is bonded to a 2-carbon piece. Carbon 4 is bonded to a 1-carbon piece. How many products would you get? You'd get 2 different enols and 2 different ketones, right?
So would the BH3?
BH3 would also give you 2 different ones. Yep, wouldn't be selective either.
Yeah. Okay.
Or right? And then their corresponding enols as well. Right? So you get 2 different products, right? You gotta be careful. The alkyne is not symmetrical. This is an internal alkyne, it's not symmetrical. Right? You get 2 different products.
It's not going to be like regioselective.
Right. It's not
because the
regioselective.
carbons are both secondary,
Right.
but they can end up on either carbon.
Right. So there's no preference. There's no regioselectivity, right? 3 and 4, right? It's not like they're one's right in the alkenes, right? We could always look and say, well, one's more substituted than the other, maybe, right? But even then, if you go back and look at the alkenes, you get more read. If we were very selective on which ones we picked and how we picked them, right? So right, 3 and 4 are not the same, and there's no way to differentiate them, right? Because they're both just bonded to one other carbon, and so there's no real preference there. All right, so let's look at a terminal alkyne. First, we're just going to have it react with H plus with water. And we'll show the same example with H plus water and mercury, and how mercury essentially helps it make it go faster. Right? Mercury is a catalyst in usually these cases. So the first step is this pi complex formation. And I know we only draw 1 arrow. I mean, I said if you want to draw the second arrow, doing this, that's fine. I'm not gonna. Right? Mechanisms aren't perfect. Right? But the point is, you got to get to some sort of intermediate that explains the resulting product. Right? So we call this a pi complex. It's not perfect. It's not ideal. But it's the best model we have to explain the product we get. Right? Which, you know what, that's mostly chemistry. So we got this pi complex, which is just like the bromonium ions we've seen. Just like the chloronium ions we've seen, right? Also like the mercurium ions we've seen. Right, where you do a trans attack, so you get a trans product, trans addition, and we always want to attack, right, which carbon here? Attack the more substituted carbon, right? So we always attack the more substituted carbon until I tell you different, and I will tell you different eventually. There'll be different reagents that'll make us do that. We attack the more substituted carbon, carbon 2. Those electrons go up then. The key point here is make sure you show me that that methyl is now in a different place. I want to see this being trans in this intermediate. Oxygen, another key point, the lone pairs of the nucleophile here, right? These OH bonds do not break, right? They're still there. Only the lone pair is attacking, right? We always want to balance our charge. There'd be an H here, and there always was an H there originally, right? H plus is actually a catalyst in this case. So if you have a catalyst, you know you're not done until you've regenerated it. And you could even draw it as, if you want to, right? This looks like an enol, right? Acid catalyzed enol kind of thing. The book will show it as, I mean, I don't know, we can do it a couple different ways. I think it's just easier to show these electrons attacking that H, these electrons going down. Right, if I number my carbons again, because I should be doing that. 1, 2, 3. There's now a pi bond between 2 and O. There's still an H here, the plus charge on the oxygen, balance our charges. And now there's 3 H's here. And we know we're done because then we can, essentially the hydrogen just leaves, right? And we've regenerated our catalyst, right? The hydrogen, it says here, oxygen, take these 2 electrons, I'm just going to be H plus.
Does it matter if, since we have water, can we draw it as water taking the hydrogen?
You certainly can.
Okay.
You could draw it as water taking the hydrogen if you want to, absolutely. Yep, and then it'd be H0 plus at the end. Totally fine. Totally fine. All right, let's look at mercury. Very similar to the one we just did. Hg2 plus, H plus, H2O is floating around. Again, first step, we're going to make a merconium ion. Hg plus, number by carbons 1, 2, 3. 1, 2, 3. Water's around. Which carbon should water attack? 2. Makes sense. That means the 2 mercury bond is breaking. It's broken. So now you see the mercury and the water are trans to each other, right? Because we get a trans addition. Right? Get a trans addition. And we know once we get the mercury on there, the first thing you should be thinking about is how do I get the mercury off? Right? Don't want to die. But first, let's do a tautomerization, right? We know at the end of the day, carbon 3 here is going to need H's. 1, 2, 3. So let's put an H on carbon 3 and make a pi bond between 2 and O. Okay? Still got mercury there. One, 2, 3. All right? Want to get rid of the mercury, right? Want to get rid of the mercury. So let's get rid of the mercury, right? Oxygen has a plus charge, right? Oxygen has a plus charge. Let's push electrons towards it. Let's give it electrons, right? Mercury is a metal. Is mercury very electronegative? No. So let's have mercury, this mercury carbon 3 bond break, and have these electrons go back up to the oxygen. Let's push electrons to the oxygen. So we've remade, right? We've remade the enol, but at least we got rid of the freaking mercury. Right, it's actually 2 plus again, because it was plus here. But we told you not to worry about the oxidation states of the mercury. It's not a big, don't worry about it. It's not a big deal, it's a big deal. But, right, so now we're back in enol, right? Now we're back where our comfort zone is a little bit, right? But this is a little different, right? This enol is catalyzed by the acid. Right? We have H plus in there. So let's use the H plus, right? H plus is a good electrophile. 1, 2, 3. And we guys know pi bonds are good nucleophiles. So let's have this pi bond attack the H plus. And I can do this in 1 step or 2 steps. I'm going to draw the 1 step version. Let's have those electrons between O and H go down between O and carbon 2. Do you see that? So what happened here? We have a new pi bond between oxygen and carbon 2. And a new CH bond on carbon 3. And we also made H plus, right? This hydrogen right here became this hydrogen, right? The H plus. This one lost the electrons. 1, 2, 3. So that's the difference between mercury, right? Essentially, it's a second tautomerization you have to do. So the second time you have to turn an enol into a ketone. Second time you have to do it. Okay. So, yep. So let's look at number 14. This is a good one because it features N-butyl lithium, which we've seen as a strong base to deprotonate terminal alkynes. Right? This is N-butyl lithium right here. Right? This carbon has a delta minus or even a full minus charge. And we're going to show it reacting with this. And the question is, what kind of arrows would it have when we know these are the products? Right, which way would the equilibrium lie? Right? So then the lithium is actually here. Right? And now the thing to remember is, right, a carbon-lithium bond can be drawn like this, like a bond, like a covalent bond, or it can be drawn like this, like an ionic bond. Right? Same idea, right? So what is different here? So here we have a carbon with a negative charge. Let's just say, right, I could draw it, or I could draw it like this as well. Right? It's the same idea. So when you're given these problems, right, if you have no idea, the first thing you should look for is differences. So what's different, right? What's different here? So if I looked at it, I would say, well, there's negative charges. One is a negative, this guy's a negative charge, and that guy's a negative charge. So which one's happier with a negative charge and why? So this one's this negative charge, these 2 electrons are in an sp orbital, right? Because this is sp hybridized with 2 pi bonds, 2 p orbitals, right? Sp hybridized has 2 sp orbitals and then 2 p orbitals. What's the hybridization say of N-butyl lithium's carbon?
sp3.
So where are those lone pairs at? What molecular orbital are those lone pairs in? They're in an sp3 orbital, which is of course farther from the nucleus, right? And opposites attract. So that means this is more stable. So equilibrium is going to lie towards the more stable thing, right? So your arrow you should pick would be going more this way, and it'd be less this way. Right? But it's a nice one because it features, right, N-butyl lithium, a new base you've learned, right? Terminal alkynes, right? That CH, and understanding, right? Well, why does this reaction even happen? Right? Because we know this is a strong bond. Why would this even happen? Right? It happens because the stability of this, because it's in a molecular orbital, that's sp, which is close to the nucleus, opposites attract.